All right, this is what we're looking at today.
Oh, I thought you just.
Lecture, no homework, but you are required to make a crib sheet for the midterm. Does everyone know what a crib sheet is?
Nope. Just like cheat sheet.
It's a cheat sheet, yeah. So 8.5 by 11, one piece of paper. You got to get it all on one piece of paper. And everything on there that you think possibly could be on the test or helpful to you. So it's an individual thing, right?
Is it still gonna be open?
Yeah, it's open book, open notes, but I like the concept of a crib sheet because it makes you organize things on a piece of paper. You don't have to use it during the test. That's fine. Just you're gonna submit it for points, right? Instead of homework. Yeah. Huh? You can use front and back. I always like to say you can use front and back and the edges if you really want, but that's tough. Yeah, and again, it's up to you what you put on it. I'm not going to grade whether you have everything on it or not. That's not for me to decide. Maybe, maybe inertia is something you got, you fully understand, you don't need it on the crib sheet, don't put it on there, right? So it's an individual thing, but there's no homework, there's just that. Good? Any questions on that? Nope. All right, midterm Thursday, that'll be 1 hour. Probably 3 to 4 problems, and then you'll have a take-home portion that you'll just walk out of here with. Now, whether I let you choose which ones you take home and which ones you don't, I don't know how I'll do it. I've done it all kinds of ways. So if I put one problem on every piece of paper, right, then you can just tear off pieces of paper and take the ones home you want. It's kind of fun, gives you a little bit of freedom.
It's pretty much everything that we've gone over the entire.
Yeah, we'll do a review kind of towards the end of class, but yep. It's 8 through 11, not all of 11 because we haven't done all of chapter 11, but yeah, 8, 9, 10, and the first part of 11. But we'll do that in a bit. Yeah.
Is it the last week to turn in homework for the past 2 weeks?
No, I let you do that up until like week 7. Yeah, and then I shut it off at some point, but it's still open. Okay, there has been requests for this one. So this can actually count, right, as a review, obviously. Poisson's ratio could be on the test. So this problem said, given these loads, calculate, I think the total change, is that what it said? Compute the dimensional changes for the steel bar when subjected to the loads shown. Then it said the proportional limit of the steel is 230.
I have a quick question. Is elongation the same as deformation?
Yep.
Okay.
Absolutely. Same exact thing. So what's this? Proportional limit.
The breaking point, it's at the top of it.
Yeah, it's not the breaking point. What's
Not
the
breaking point, but it's the.
And it's not the yield point.
Yeah.
It's the proportional limit. Right?
It's not the yield. Oh.
So remember the graph can go straight and then it curls over. Typically that's the yield right there. The end of the straight line is the proportional limit. End of the straight line. Some designers use the proportional limit, some use the yield. It's just a personal preference. They're very close to each other typically. Like, do you remember what the yield is for this in the metric? The yield is 250. The proportional limit is 230. So if a designer's using 230, they're just adding a little bit of safety, right? A little lower limit than, and why do they give it to us on this problem?
To know if it's gonna.
Yeah.
Snap.
Yeah, to know if it's even something we can calculate. So if you're asked to calculate deformation or elongation, either one of those words, you got to know that it's within this limit, that it's in here somewhere, the stresses, right? So when they give you this, and if they give you the material, they give you all this stuff, right? Like I don't have to say the proportional limit is this, I could just say it's mild steel. Then you get all that information from the table. So this is just saying check the stress first. Before you go calculating elongation, check the stress. So how do we do that?
You.
Yeah, you were right.
You know,
I don't even know that I'm gonna. Oh, I'll write it down because of our crazy units, right? So stress. P over A, which one do you want to check? Because there's
X.
multiple, right? Yeah, there's this one. There's this one. I don't know if they called it Y. I'm gonna call it Y. Actually, this would probably be Y. This would be like Z. Anyway. Yeah, so we can check the first one. That's 265.
So
Kill-
if we converted it to 1,000 first.
And we should, yep. So I'll do that right now. 1,000 newtons per kilonewton, right? Over the area. What area is this acting on?
The 100 by
The
25.
100 by 25, yep. So I'm gonna put in 0.1 meters by 0.025 meters. Right? Because that gives me newtons per meter, that's pascals. Anybody have that number?
106 or megapascals. But
Yeah, you converted it on me.
sorry.
1 divide 0.025 divide 106 million. 106 million pascals or 106 megapascals, right? So the number I get is that big number, and mega is to the sixth, so it's 106, and that is that under the proportional limit? Absolutely, it's good, right? What about the other one?
The Y.
Yeah, the 600 is acting over what? 450 by 25?
Yeah.
Yeah. So same kind of thing, you should check it.
So a good way of visualizing that is just saying like the area of that one face that it's acting on.
Yeah, that's.
Yep. And anyone have that number? I get 53 megapascals.
53.3.
Yep. So the other one, I'll write as the 600 was 53.33 megapascals. This is the 265. Some kind of notation to keep track of those. Again, you're just checking stress levels. That's all. That's the only reason this is given. Is we cannot calculate deformation if the stress is over the limit. It's not predictable. Cool. Now, what do we do? Purple. Green,
Formation.
purple. Yeah, so now we have to go through this thing. And we have to figure out like, oh, how much is the deformation? That's what they want to know. So Poisson's ratio is the relationship between the axial and the transverse. We have to find the axial first. And they're independent processes, right? So how do we get the axial change? You want to remember that formula?
Area over length. Or no, excuse me, it's
So elongation is
deformation.
PL over AE.
PL over AE. Right, and I'm gonna put A for axis, or I could put X. Because this is gonna be this change. We're gonna stretch it, right? The 265 is gonna stretch this piece of steel. So that's the first thing we want to calculate. From that, we can go after transverse. effects. Then we have to do it again for the 600. Because then we can calculate this axial change along its axis and what happens to the transverse. And then we got to either add or subtract and figure out like which one's helping, which one's fighting, which ones, right? So we need to keep track of decrease and increase. Like you guys did so good on the quiz. Everybody did great on the quiz, but many of you forgot to tell me whether it was an increase or a decrease. And I didn't mark off for that, but this is super important that we know what happens here, right? Okay. So this is clearly going to be an increase, right? We're going to stretch. All right, I'm trying to make some space here. How much is the load? I'm going to put in 265,000 newtons. Right? E, L, A, E. What's our length? 450. If I put in, yeah. I'm gonna go with meters. By putting in 0.450 meters. I'm gonna go with newtons and meters.
I think that was my issue. So I was thinking-
Because pascals are gonna come into play here somewhere. And I just want to put in Newton meters squared. All right, and this is over area. What's my area? Yep. 0.1 by 0.025. And then E for this material. Did they call it? Hopefully they called it like
207 803. There's a mock-up that would be different for us.
they just called it a steel bar.
Yeah,
Yeah.
I could get David.
So E values, I think, are all the same for most of the steels in the back. 200 is what I have. 200 times 10 to the 3 megapascals. 200 times 10 to the 3. So this is the hard part. 200 times 10 to the 3, 1, 2, 3. And then it's megapascals. So it's 200,000 megapascals. Right? Everyone get that?
Yeah.
So it's really 1, 2, 3, 1, 2, 3.
Yeah.
6 more zeros. Newtons per meter squared to get to pascals. A pascal is a Newton per meter squared. So like, wow, that's a lot. So it's really 200, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 200 e to the 9. That's how I would write it without all those zeros. But and then we have newtons. We have everything that's going to cross out. Newtons and newtons are crossing out. Meters squared, and we're left with meters. Okay, we're left with meters. All right, see if we can crunch this. I get 0.02. I'm gonna round to 4. meters or 24 millimeters. 0.024 meters. And this is axial. Anyone else get that number?
I think it's 25.
You think what?
I just.
Nobody else gets my number?
I did it wrong.
Yeah, I get the same number again.
Giving. That was a total of like. I probably just.
Yeah, I get 0.00024.
Maybe I'm forgetting the 200. Let me do this again. So it's 200 e to the 9. I might have mucked that up.
2 weeks.
265. Yeah, that's what I was doing. Yeah, 3 zeros. Agreed?
Yep.
0.2 millimeters. Very small change. Ooh, that means we're gonna get some super small changes in the other directions.
Yeah.
Very small change. That better?
Yeah. I threw a 5 in there. I thought it was 250.
Yeah, I didn't. I was doing 2 e to the 9,
And
not
then I was doing
200,
negative 9.
not 200 e to the 9. All right, so now to get the transverse, we use Poisson's ratio. So the transverse strain is equal to Poisson's ratio times the axial strain. We just move this over. So the transverse strain is equal to the Poisson's ratio and the axial strain. And we know strain is delta over L. So the delta of the transverse over the L of the transverse equals Poisson's ratio, the delta of the axial over the L of the axial. So delta over L is strain. So I just subbed these in. And we know, like this is this. And we know L, the original length was 450. So all this is known. We know Poisson's ratio, we can look it up. And what we want is a change in the transverse, and we just have to put in a transverse dimension. So this will be the only thing we don't know. And again, we're just doing it for the 265. This is all just for the 265. All right, so I'm going to put in what we know. We don't know the transverse change. We want to know that. We need to put in a transverse dimension. So we have two of them. We have 125. You got to do them individually to figure out how much they change. I know. It's a lot. You can't do it all at once. You got to do them individually. So we'll do the 100 first. It's 100 millimeters. So I'm going to use millimeters. What's Poisson's ratio?
0.25.
0.25. What was our axial deformation? 0.24 millimeters. So I put it in millimeters because I have this in millimeters. And then the original length of the axial. So this tells you how much the change happened to the 100 millimeters. And this is going to be a increase or a decrease? Decrease. Yeah, the 100's going to shrink as we pull on this thing. All right, let's see if we can calculate that. You want to get a number? Yeah. So in the long axis, it changed 0.24 millimeters. In the transverse of the 100, it changed 0.013 millimeters. And I'm going to put a negative for decrease, and I'm going to put a positive for increase there, just to keep track of things. So to get the 25, how much the 25 changed? We just put in the 25 because the axial strain doesn't change. These numbers don't change. Poisson's ratio doesn't change. We just need the 25 in here. So that'll give us the change in the transverse of the 25. I get 0.0033.
Why did you put a theta?
Decrease.
Okay.
Just trying to
Oh.
remind myself that, hey, that's decrease, that's down. Right? And this one is an increase.
And it's always relative to its axis.
Yep. Does that help?
Yeah,
That's one load.
you have to.
Guess what? You got to do it again for the other load. Same exact process though. Then you can add and subtract. Right? But this is done now. We have the axial and we have the two transverse changes based on the 265. So now we got to do the exact same thing with the 600. So let's do one. We'll do the axial change. And then we would have the total amount. We could figure out the total amount the 100 would change. All right. So back to axial. This time it's going to be of the 600. And that's PL over AE. And the load is going to be 600,000 newtons. The length, the axial length in line with this is 100. Or 0.1 meters. So axial is always in line with the load. The area that it's acting over, that's this area here. 450 by 25. Put it in meters. And then it's the same E. Ooh, goodness. We're getting really small. Yeah.
E to the.
Yep, so it's 0.00004 zeros 267. And that's in meters. So if I move it 3 places, it's 0.0267 millimeters. Is that an increase or a decrease?
Decrease.
Yeah, squishing it. So it's definitely a decrease. Minus. And that's in the Z direction is what I called it originally. Or transverse to the 265 force, right? So 265 was doing what to the 100 millimeters? It was decreasing it. 600 is doing what to the 100 millimeters? Decreasing it. So that's an additive negative. It's an additive decrease, right? So we have to find that number. It's right here, 0.013 and the 0.0267 get added together for the full change of the 100.
And you do have it, you don't have a negative.
I don't do what?
You input the negative?
No,
Okay.
no, that's just for your head to keep track of decrease and increase.
So
So,
for the 600, you don't need to do the transverse.
Yeah.
Or you do.
but not for the 100. Yeah,
So it's one.
so what's the transverse dimensions to the 600? Aiden?
100.
No, the transverse. Transverse to this is 450 and 25.
Yeah.
Yeah. Not the 100. 100 is axial. Yeah. So that's why we can get the 100 change right now
Okay.
without having to do the transverse, right? To get the change in the 25 and the change in the 450, we would have to do the transverse. Yeah. Good times. So right now, the change in the 100, so the 100 millimeter change equals the 0.0267 and what we found up here, 0.013. So that's a decrease. And we can get that number because we don't need the transverse for that. Point 0.03, 0.040, I would round it. One of our answers.
Oh,
Whew. Crazy stuff. Like if I gave you this problem on the test, this it could be the only problem because like there's no time for anything else. So I definitely wouldn't give you this deep of a problem, right? I want to know that you know what Poisson's ratio is. So I don't want to spend probably another half an hour doing the transverse to the, I think you kind of get it and you have this recording to go back through. But that's how you do it. It's nutty. Very small numbers.
yeah, it didn't help that it was in the trip. That is.
No, that's a little mind boggling. But we have to get
Yeah.
more comfortable with it for sure. Questions? It was like. It's perfect. Just blow everybody's mind up right before a midterm. That's great.
I'm glad we went over it though, because I was,
Yeah, I think you kind of get the flow of it now. You got to find everything axial first before you can then go for the transverse. And then it's just Poisson's ratio and this relationship right here. So like, honestly, this kind of thing on a crib sheet is golden because you're going to write it down the way you understand it on the crib sheet. If you go to the book and you look it up, Poisson's ratio, and then you're going to be like, oh, what is all the, this is different than the way I understood it kind of thing. So to get some notes down that are in your language for whatever it is you're working on, it's golden. All right. Good? Good enough? Helpful? Hopefully? All right. Any other homeworks? How was thermal?
thermal was so easy.
Isn't that nice?
So nice.
It's like two simple equations.
Yeah.
Don't switch them by accident is my only suggestion, right? Alpha E delta T, if it's got E in it, it's going to give you a stress, PSI, right? Because that's the unit. Alpha L, if it's got L in it, oh, that's elongation. When do we get thermal stresses? When it's confined. If it's free to grow, no thermal stresses, none. So if the problem says consider thermal stresses, yet it was just, something that was free to expand, the answer to that is there are no thermal stresses. If it's fixed, locked down, then thermal stresses occur. So yeah, it's a pretty simple.
If there was the last problem, if it's free, but then it can go up.
Yeah,
or something,
yeah.
then it does hold it.
Yeah,
gain
so-
thermal stresses.
It was like this and it was blocked down and then there was some kind of gap.
Yeah.
Yeah.
0.5 millimeters.
Yeah, so it doesn't really matter what the numbers are. But what you have to figure out is like how much temperature does it take for it to touch, like to expand and touch. So would you say that was
0.5 millimeters.
Yeah. So our equation is elongation is alpha L delta T, right? So what we want to know is how much delta T will it take to get to 0.5 millimeters, right? And then how long was this?
I think it was a meter.
100 millimeters, 1,000 millimeters, or 1 meter, right? Yep, 1 meter and then 0.5 millimeters. Yeah. So then 1,000 goes in here. And then delta T. So that gives you like how much temperature will it take to expand until it hits? Because none of that temperature produces stress. Does that make sense? So the 0.5 kind of becomes the delta, and you gotta calculate like how much T does it take? What's alpha for the metric system? For, what is this thing, copper?
It's 1.67. E to the
Copper. I get 93. For copper. For the coefficient. 9.3, 10 to the minus 6. Oh, wait, was I looking in the wrong one?
The calculate the stress developed in the bar due to the temperature rise of 50 degrees Celsius.
Yeah, I did the wrong, I wrote the wrong coefficient there.
Yeah, I think it's 60, so.
It's 16.7, 10 to the minus 6.
I've done that so many times.
Yeah, it's easy to do. Metric. 16.7, 10 to the minus 6 millimeters per millimeter per degree Celsius. All right. So delta T equals. So we take the 0.5, divide by the 16.7, 10 to the minus 6, divide by the 1,000. I get 29.94 degrees. 29 degrees C. And the total temperature change was 50 degrees C. Right? So the first 30 degrees does not approximately 30 degrees does not create thermal stresses. Because it's free to expand. But then it hits. So the rest, the difference between the 50 and the 29.94, what is that? 50. So it's 20.05, 20.05 degrees C creates stress. Everyone see that? You had to figure out like, well, how much temperature did it take to get there? What's left over is going to create thermal stresses. So then you pump it into the thermal stress equation, which is alpha E delta T. Same material, so alpha is the same, 16.7 e to the minus 6. E for the metric system for copper is 103 times 10 to the 3rd megapascals. Ends up to be 103 e to the 9. Or you can just leave it in megapascals, right? Because that's going to be your stress in the end. So however you want to do that. 103 e to the 3 megapascals. You can just leave it in that. And then that'll be the unit you get. And the delta T, the leftover, is 20.05 degrees. Either one of these works. This just gives you megapascals directly. I get 34.49 megapascals. Get it? How it works though?
Yeah.
Yeah.
That would have been different. round, which makes-
So then if you had thermal stresses and you had like a load stress, you can calculate both of those and figure out what's going on. So if something is loaded in tension, from that load, you can calculate the elongation, right? If it's free to expand, then, and the temperature goes up like a delta T of 120 degrees F, then you could also calculate how much it would expand due to the temperature. And those two would be additive. You would add that up, right? It's going to expand due to this load. And then it's going to expand some more due to the temperature rise.
You do the temperature after the run.
Either way. Yep, doesn't matter. I would not do the temperature after. I'd use the original length. So if you did the temperature after you did the load, then the thing would be longer and then you'd add the temperature. Not really, because everything gets installed at a average temperature and then things happen to it. Loads, temperature. Yeah. All right, good. Well, let's think about the midterm. Starting with chapter 8. So one good strategy is to look at the chapter summaries. So if you go to the last part of chapter 8, it'll tell you what was in that chapter. So, inertia. Right? How did we find inertia and the transfer formula? Those are the two things. So you could have a problem where you calculate the inertia. And that could make you calculate the centroid first and then go for the inertia. I won't make it a very complicated shape, but it could be like a structural shape, you know, and then something added to it. That's usually what I do. That makes you look up structural stuff. I'll have all the tables and everything copied for you to use during the test. So the test is going to feel really thick, but it's got a lot of tables in the back, so it's not that bad. So definitely refresh yourself on how to calculate an inertia if you need to. But that's all we did. We did not do radius of gyration. We did not do polar moment of inertia. We did not do those two. There's no reason to do those until you get to torsion. So like, I don't know why they do it early, because then they don't use it until you get to torsion. Torsion is twist, right? It's how much something twists. All right, then we got into the kind of the nuts and bolts of it, which was stresses. Stress and strain. So that chapter summary starts with just regular old average stress, P over A. And then shear stress is P over A. And then we did elongation. And we talked about modulus elasticity and how to use it. Definitely going to be those on the test. Like you'll have to calculate a normal stress, a tensile stress, a compressive stress, a shear stress, any of those. What's the difference between tensile stress and a shear stress?
Tensile's good.
Tensile pulls perpendicular to the cross section. 90 degrees, right? So like 90 degrees, it's pulling away from the cross section. Shear stress, everything lines up. The area and the load are kind of in line with each other. They're parallel. And it's going to shear it off. So sort that out. It's P over A. Everything is P over A. We did not do shear modulus elasticity. So if you're looking through the book and you're like, oh, I don't recognize that, we didn't do it. Again, why do that until we need it? So I bring those in. It's a material property. It's in the back of the book, just like E. So we did a lot of this. Chapter 9, we did a lot of. So I would expect at least a couple problems in class on this kind of thing. So look back over your homework and your notes, organize that thought. Big part of this test is categorizing the problem. Like, oh, this problem is a compressive stress problem, or this problem is a inertia problem, or this problem is a elongation problem, right? There's our elongation equation, PL over AE on the axis. Then chapter 10 was the material chapter. So there could be a question about, you know, the stress strain graph. Like, what is the proportional limit? How's it different than the yield limit kind of thing? So all these limits are here. We didn't go over all of these different, because not every material has it. This is like the perfect graph, and this is like mild steel graph. That's why we love mild steel. It has this whole graph, but a lot of materials don't have that. So really the points I care about is that this straight line region, the proportional limit, and the yield, not the upper and lower yield, just the yield. You know, and what they mean. Proportional limit is just the top of the straight line. The yield point is where it permanently yields. Now it's deformed, right? That's super important.
And it's different, there's different graphs for tensile versus compressive.
Now, we do them all in tensile.
Oh, got it.
We pull all material. There's different graphs for every material. Yeah. Mild steel has a great graph. You know, titanium's graph looks more like this without the little hook on top. It's just a straight line up and then it explodes. So it doesn't do a lot of yielding.
Yeah, I was thinking of concrete.
Yeah, concrete doesn't, it's a straight line graph. Yeah, doesn't deform well. Yeah. And then the other thing in this chapter was factor of safety.
Not gonna be a lot of questions.
Chapter 10?
Chapter 10.
No, I can integrate all of chapter 10 into any other question. So like I can just add factor of safety to any problem I give you. And that kind of deals with factor of safety for chapter 10. And if I give you the yield, the problem gives you the yield point or proportional limit, that's chapter 10, right? So no, I'm not going to ask you the pros and cons of mild steel.
No.
All right, and then we had chapter 11. And we only did a couple out of it. We did Poisson's ratio and thermal. So we have more to do out of 11, but we didn't get there. So Poisson's ratio, and then the two thermals. We will do multiple materials and we will do stress concentrations, but that'll be after the midterm. So probably, I'm guessing 3 to 4 in class, 3 to 4 problems in class. And then probably 2 to 3 take home. And you probably have to do them all that on Thursday, so if that's a problem. Like, you leave this class and you gotta go to work for 1,800 hours straight, you know, Colton. Then you just need to communicate with me about that. So the 3 to 4, my suggestion there is really keep track of your time. Because you have an hour, it's like 15 minutes a problem. Don't spend 30 minutes on one problem and then not get to the other 3. Look them over, look all of them over. Think about the ones you want to work and the ones you want to take home, if that's the option. And then knock them out.
What is the time limit for homework?
That day, you have the rest of the day. So like till midnight, Thursday. No time limit. Good? It's gonna be a good time. It's always a fun one. All right, we are done.
When are we, are we supposed to just have the crib sheet?